Hi everyone, I am Neil Trevett. I work on developer ecosystems at NVIDIA. I am president of the Khronos group and OpenCL chair. And I'm happy to have the opportunity to speak here today at IWOCL on behalf of the OpenCL working group and to give you a State of the Union update on the latest developments in the OpenCL ecosystem. A lot has happened since IWOCL last year. OpenCL 3.0 was finalized and released in September, creating a baseline for pervasive deployment of new functionality beyond 1.2, and including new subgroup operators and extensions for embedded processors. Although the specification was released only a few months ago, there are already multiple conformant OpenCL 3.0 implementations shipping today. The working group has been improving the OpenCL conformance test suite and issuing regular specification updates, including the new OpenCL 3.0.0 here at IWOCL, which includes new extensions that we will cover briefly later in the presentation. To help developers more easily learn and use OpenCL, the new OpenCL guide has been released, and the OpenCL SDK improved with a loader that supports loadable layers. In the area of kernel languages, the C++ for OpenCL open source front-end compiler is gaining strong momentum and benefiting from Khronos' deepening interaction and cooperation with the LLVM community. Another layered implementation is joining Google's SPIR-V OpenCL over Vulkan compiler. Microsoft's OpenCL 12 is bringing GPU accelerated OpenCL to any PC with DirectX 12. On desktops and in the cloud. Lastly, the working group is starting on the next round of roadmap discussions, and we hope to get feedback into that from the developer community here at IWOCL. So let's have a look at some of these developments in more detail. But first, as is now the IWOCL tradition, we have updated the trend line of the number of open source projects on GitHub using OpenCL as one indicator of how widely OpenCL is being used throughout the industry. And good news, there are now over 12,000 OpenCL related projects. That's a tripling in the last 4 years, and the upward slope is accelerating. So let's talk in more detail about OpenCL 3.0 that was finalized and released in September 2020. OpenCL 3.0 enables hardware vendors to focus their resources on driver functionality that their customers need by making all functionality beyond OpenCL 1.2 optional through API queries and language macros. OpenCL 3.0 also removed the OpenCL C++ language from the specification and recommends use of the C++ for OpenCL open source front-end compiler that generates SPIR-V code. Existing applications can be easily moved to OpenCL 3.0. OpenCL 1.2 applications require no changes, and OpenCL 2.x applications also require no code changes if all the functionality they use is known to be present. To ensure future portability to any OpenCL 3.0 implementation, developers are encouraged to query for any optional functionality that they use. In terms of adoption, OpenCL continues to be the most pervasive cross-vendor open standard for low-level parallel programming. OpenCL is deployed by GPU, DSP, and FPGA vendors and used by a wide number of applications, engines, and libraries, as well as acting as a back-end target for languages, compilers, and machine learning stacks that need a portable API to reach into hardware acceleration, including Khronos' own SYCL and OpenVX. For example, almost all mobile inferencing engines from companies such as ARM, Qualcomm, Intel, VeriSilicon, Synopsys, TI, and Xiaomi use OpenCL as an acceleration backend. When deciding between OpenCL or GPU APIs such as Vulkan, many developers that don't need graphics rendering find that OpenCL provides a simpler programming model, more advanced compute functionality, a lighter weight runtime, and more rigorously defined numerical precision that can be critical for many compute applications. There are additional hardware implementations this year. For example, Cowray shipping an OpenCL 1.2 on their intelligent embedded processors, and Cowray are actually speaking here at IWOCL, so please check out their presentation. And Cowray is not the only hardware vendor with new OpenCL implementations. Even though OpenCL 3.0 was only finalized a few months ago, Imagination, Intel, and NVIDIA are already shipping conformant OpenCL 3.0 implementations, and there is a growing number of hardware and software vendors that have become OpenCL 3 adopters, and they will be able to ship implementations when they are ready. As we mentioned, OpenCL 3.0 removed the OpenCL C++ language from the specification and recommends use of the C++ for OpenCL open source front-end compiler that is supported in Clang, it leverages LLVM, and it generates SPIR-V code. C++ for OpenCL is fully compatible with OpenCL C and also enables developers to use most C++ 17 features in OpenCL kernels. The new CXX for OpenCL extension enables an OpenCL driver to ingest and compile kernels written in the C++ for OpenCL kernel language. Several new extensions were released alongside OpenCL 3.0, including asynchronous DMA extensions that enable DSP-like embedded processors to transfer data between global and local memories via DMA transactions. This new functionality complements previous one-dimensional operations by supporting complex memory transfers and by enabling multiple asynchronous transactions to run in parallel using fences for synchronization. There is significant activity in continuing to extend OpenCL functionality for DSPs and other embedded processors. Here at IWOCL, we are continuing our regular OpenCL specification updates with OpenCL 3.0.7 that, in addition to the normal clarifications and formatting and bug fixes, defines a number of new extensions, including extended bit-level operations, new queries for suggested local workgroup size and PCI device information, and enhanced SPIR-V support for debugging and linking. The new specification is available on the OpenCL registry today. The OpenCL Working Group is also expanding the OpenCL SDK to increase its value to developers. And although we're making good progress, this is still an ongoing project, and any community contributions are also very welcome. Our goal is an SDK with a comprehensive user guide and a set of samples that use the SDK headers and build system with full CI. Over time, we intend to also include utility libraries, and we are very interested in which libraries developers would find most useful. And most significantly, we already have a new loader that enables loadable layers that are available today. And there are many more details about the SDK in the SDK tutorial presented by Bryce Vido from Argonne National Lab here at IWOCL. The industry trend of layering APIs over other APIs through the cross-compilation of shading languages continues to grow. For developers, a layered API can enable their application to run on platforms that don't support that API natively, reducing platform fragmentation. Layered APIs can also be invaluable to platform vendors to enable additional content on their platform without incurring the support load of an additional kernel-level driver. This layering trend is being fueled by the increasingly robust open source compiler ecosystem leveraging Khronos' SPIR-V, making SPIR-V an ever more central part of the Khronos standards family. SPIR-V is an intermediate language representation that includes heterogeneous parallel processing and graphics operations that can be broken down into instructions for GPUs and other processors. SPIR-V is the only language directly ingested by Vulkan, and it can be imported into a growing number of OpenCL implementations. SPIR-V enables the hardware and compiler communities to innovate independently, as front-end compilers can simply generate SPIR-V code to be ingested and executed by a wide range of runtime APIs. In addition, API runtimes that ingest SPIR-V eliminate the need for front-end compilers to be deployed in embedded systems. And here are two examples of layered OpenCL implementations leveraging SPIR-V. The Google SPIR-V compiler enables OpenCL kernels to be compiled and executed on a Vulkan runtime, which, together with the CLVK runtime API translator, enables OpenCL applications to run over Vulkan. SPIR-V is already being used to ship demanding OpenCL applications on Android, such as Adobe's Rush video editor, that has over 200,000 lines of OpenCL C running on Vulkan with full GPU acceleration. And since IWOCL last year, Microsoft has released the OpenCL on 12 open source project to layer OpenCL over Microsoft's DX12 API. With Collabora's assistance, Microsoft leverages the Mazer open source graphics framework to translate SPIR-V through Mazer's near intermediate representation into DXIL, that's DirectX's intermediate language. CL on 12 will enable accelerated OpenCL wherever Windows 10 with DX12 ships, including on ARM-based PCs and in the cloud, and should soon be officially conformant. So now that OpenCL 3.0.7 specification has shipped, what is next in the extension pipeline? The OpenCL working group has been working on several extensions, including integer.product and interop functionality that are already in ratification and so will be released in the second quarter of 2021. In particular, the set of extensions for external memory sharing will enable OpenCL to interop with other APIs, such as Vulkan, by importing handles to memory and semaphore objects, and then using semaphores to wait and signal the other runtime to coordinate the use of shared memory. Interop between OpenCL and Vulkan has been in strong demand for both mobile and desktop platforms, and these extensions can also be used to interop to other desktop APIs in the future, such as DirectX 12. The interop extensions have been released provisionally for developer feedback before we finalize, so please let us know what you think. Looking further ahead, the OpenCL working group is now discussing the medium to long-term extension roadmap pipeline that contains a diversity of potential functionality. Some of the most active discussions are around command buffer recording and replay, which separates command creation from dispatch via the concept of command buffers, avoiding unnecessary overhead when constructing commands that are enqueued multiple times, which can be used to significantly speed operations such as inferencing. The working group is seeking input and feedback from the developer community on which extensions should be prioritized and whether any needed functionality is missing from the roadmap. And to enable and encourage feedback, we have posted a feedback issue on GitHub where we welcome any comments. Ensuring that needed functionality is on the extension roadmap is particularly important, as only extensions that are proven to be useful and widely adopted will be lifted into future core specifications. If you would like to work more closely with the OpenCL working group, but your company is not able to join Khronos to participate in the working group directly, then we invite you to apply for membership in the OpenCL advisory panel of industry experts. Advisory panel membership is available at zero cost to companies or individuals that are willing to sign the Khronos NDA and IP framework agreement. The OpenCL working group shares draft specifications with the advisory panel for detailed feedback and design suggestions. The advisory panel is chaired by Mate at StreamHPC, and we have hosted a panel meeting here at IWOCL. If you are interested to join, please send an email to the address on the slide. So that's the latest OpenCL updates in a nutshell. I hope you found this overview useful. Please come on to the OpenCL GitHub. Let us know about your experiences with OpenCL 3.0, which OpenCL 3.0 optional features do you use most often, as that helps us prioritize what features should be elevated to core. And what are your priorities on the extension pipeline, especially if the functionality you need is not there on the roadmap. So thank you, and we look forward to hearing from you.